everyone. Welcome to this lecture in Cloud. I'm Guliang Ma from Institute of Modern Physics, Fudan University. And I'm honored to host the Frontier in Nuclear Physics Open lecture series. This lecture series is sponsored by the Institute of Modern Physics, the key library and the nuclear physics and ion beam application, MOE, and the Shanghai Research Center for the Theoretical Nuclear Physics, NSFC, and Fudan University. The presentation will be broadcast live on the Zoom conference platform. You can ask questions after the presentation. The presentation is also broadcast live on the Koxiang Science platform. Today, we are honored to have Professor Zvi Lin from East Carolina University to introduce the recent developments of AMPT model for relativistic nuclear clearance. Before the talk, I will briefly introduce Professor Zvi Lin. Professor Zvi Lin is a professor of the physics at East Carolina University. He received a bachelor degree in theoretical physics from the USTC in 1991, and a PhD degree in theoretical nuclear physics from Columbia University in 1996. After working at LBI, TAMU, OSU, and NASA, he took the position at the ECU, East Carolina University. Since 2007, his main research interests lie in theoretical heavy ion physics, radiation physics, and pseudo-CT imaging generation. He is famous for the development of Monte Carlo transport model, including AMPT. In high-energy heavy ion physics, he has published more than 100 articles and received awards such as the Outstanding Reviewer of Nuclear Physics A and the Scholar Teacher Award at ECU. Now I will hand over the time to Professor Zvi Lin. Please start.
Okay, thank you for the invitation and the introduction. So
recording in progress.
Let me talk about recent developments of a multi-phase transfer model for relativistic heavy ion collisions. So the outline of my talk is the following. So I will first show the motivation, and then I will discuss the earlier status of the AMPT model at around 2019. And then we will look at the recent improvements of the AMPT model. And finally, I will summarize. This talk is based on a summary article recently in Nuclear Science and Technology. And then it's also based on individual studies with collaborators whose names are listed here, including many of you who are present here online. Here is some motivation for developing transfer models. And the main reason is that transfer models are suitable for non-equilibrium dynamics and studies. We know that for large systems at very high energies, transfer models will have many interactions, and as a result, their results are similar to hydrodynamics. However, transformer models use macroscopic particles and their scatterings and interactions. So it's a complementary approach to hydrodynamics-based models, which uses the energy density, energy momentum tensor, equation of state, or etc. So they use different language and they have easy access to different physical quantities. For finite systems or small systems at finite energies, however, non-equilibrium effects may be important, and it's natural to expect them to be important. One example is the so-called escape mechanism, which was discovered a few years ago. It's basically a mechanism to generate an isotropic flow in the momentum space by the kinetic theory response to the anisotropic shape in the overlap region. And this escape mechanism is different from the generation of flow from collective motion, which people typically think about. And that's a non-equilibrium effect. And recently, we know that small system data from, especially from LHC, seem to suggest the observation of collective flow signals, similar to those in large systems. There are many questions about them. For example, are they real signals from collectivity? Does it mean a formation of parton matter, like or even a quark plasma? Is the small system far from equilibrium or close to equilibrium? To study these, answer these questions and study the properties of parton matter or QGP, transfer models and kinetic theory are crucial because they can address non-equilibrium dynamics. So here I have a few references for kinetic theory studies. About the motivation to construct the AMPT model and further improve the AMPT model, here is some introduction. You know, the AMPT model was constructed as a kinetic description of heavy ion collisions. It's a self-contained because the model evolves the system from initial condition all the way down to final observables. And as a transfer model, typically it automatically includes production of particles of all flavors, and is automatically three-dimensional. And also it has the conserved charges, such as strangeness, electric charge, baryon numbers in the constituents, like partons or hadrons. And also, the AMPT model includes non-equilibrium initial conditions and is dynamical evolution. So here is overall simplified structure of the AMPT model. So we have two hadrons or two nuclei coming to each other, and then they will generate, after the primary collision, they will generate some kind of initial condition. And then if the energy density is high enough for the formation of a parton matter, then the matter will enter a parton cascade to model their interactions. And then when the system cools down, they will go through hadronization and form the primordial hadrons. They will continue to interact in the hadron cascade. And after a certain time, when we think they reach a kind of chemical and kinetic result, we have the final particles. And the AMPT model, in addition to providing the momentum spectra at freeze out, it will also provide the space-time coordinates at freeze out. And about the early status of the AMPT model, the source codes of the model has been online since 2004. And if you go to my ECU homepage, where the AMPT model resides on, you can see the source codes, first public in 2004, and then it has been periodically updated And these more recent versions have the feature that the string melting AMPT models in these versions can reasonably describe the bulk matter for high energy large systems. And currently, after 2015, also for the public AMPT model on the web page, the string melting AMPT model, which is applicable when we believe the formation of a parton matter, can reasonably describe the bulk matter properties, such as the low PT particle, identified particle multiplicity at RIG or LHC energies, the PT spectrum of kaons and pions in those collisions, as well as the elliptic flow, including also not shown here, triangular flow, etc. So the model can serve as a dynamical tool to study other more interesting observables. So in this talk, I will discuss recent improvements of the AMPT model, and I will focus on some of the improvements since 2019. I will focus on 4 areas. First, the inclusion of modern PDF, the parton distribution functions, and the nuclear shadowing. And the corresponding work is listed here, done a few years ago. And then I will talk about the improvements of heavy flavor production and the hadronization in the model. Then I will proceed to the local nuclear scaling that enables the AMPT model to self-consistently describe the size dependence and the centrality dependence of observables. And finally, I will show recent work on the tests and the improvements of the parton transport. So first improvements is about incorporation of modern PDF of nuclei. We know that for PQCD observables, they are, for example, the heavy quark production, they depend on the PQCD cross-section here, for example, the angular cross-section, as well as the parton distribution function, which basically tells you how many partons at a given momentum are there in the nucleus when they come in and collide with each other. And they are the parton distribution function of parton flavor I in nucleus A depends on the Bielkin X and some momentum resolution Q square of the Q. And it's related to the corresponding structure function in the free proton, which is labeled as FIP. So free proton distribution function for quark parton flavor I. And then naively it's A times that. However, there are nuclear multiplications, and the function is often written as a multiplication, a shadowing function R that depends on the nuclear atomic number. It's also a function of X and Q squared. But for the free proton PDF parton distribution function, the original AMPT model is using an old Duke-Owens set. And we know that the parton distribution function in that set is obsolete. For example, if you plot versus X, the gluon density or the quark density like U quark or D quark density as function of X, we can see that compared to the Duke-Owens curves are here for the 3 kinds of partons, but for the more modern PDF, they are the solid or the dotted lines up here. So they are much higher at small x and different at other higher x. So we need to replace the current AMPT PDF by the more modern PDF for the free product. And that it has been done in the recent work a few years ago, where we incorporated the CTEC PDF for free nuclei. And then, so this part is updated. And then we also updated the shadowing function. And we have taken in that same work the EPS09S nuclear shadowing, which is a shadowing function that depends on not only X and Q squared, but also on the position in the nucleus. This S is the transverse location of a parton in the nucleus. And here you can see the plot of shadowing function in the lead nucleus at a given Q square versus the Bjorken X and the transverse position S. And on the edge, there's basically no shadowing, but deep in the center of the nucleus, you see a much severe shadowing. So we have done that work, and then we have retuned the model parameters, because those will be needed when you update, when you have a new structure PDF function. And we have fixed those parameters, for example, the mini-jet cutoff P0, and also the Lund parameter A and B with the PP data. So as a result, we can nicely fit the PP data at various energies over a wide energy range. And then we apply the same model, same parameters to central AA collisions. Then we found this comparison. We can see that, for example, for LHC, central lead-lead collisions, the AMPT model using those same parameters overpredict the particle yields by a large margin. And also, when we look at the PT spectrum of hadrons, pion, kaon, proton, and antiproton, we can see that they are too steep. The solid lines are AMPT results, and the symbols are the data. So we have done our best, and then see that the same parameters don't work for AA collisions, for central AA collisions. So the problem that the PT spectra are soft was known and solved before when we tuned the AMPT model string melting to reproduce the high energy AA data. And in that work, we found that we need to use a very small parameter value for the Lund B parameter. But we also have a new problem now with the new PDF that particle yields are over predicted. So we are forced to do something new. And one thing we can do is to suppress the jet cross-section, and therefore suppress the hard component contribution to the particle yields. And because the mini-jet cutoff P0 could be different in AA collisions relative to in PP collisions. So we include so-called A scaling for central AA collisions to increase the P0, the mini-jet cutoff. You know, for the jet cross-section, the mini-jet cutoff is here. That's the minimum PT transfer. And if you increase this cutoff, the jet cross-section will decrease. And therefore, the particle multiplicity will decrease. So we increase it according to a power of the atomic number when you have symmetric AA collisions. And this exponent Q depends on the central mass energy root S, and is fit according to what we need to reproduce the central AA data at the high energies. And this scaling is motivated by the CGC, or the color saturation model, because there we have the color saturation scale QS, and the QS in the saturation limit scales as A to the 1/6. So at high enough energies, our QS approaches 1/6. But at finite energies from 200 GeV to LHC energies, its value increases from 0 toward 1/6. And with this A-scaling of the mini-jet cutoff parameter P0, and also decreasing the Lund B parameter to a very small value of a 0.15 over GeV squared, we can describe the central AA data in both RIC and the LHC energies for central heavy ion collisions, as shown here. So the yields are reasonable as well as the PT spectrum. Let me come to the improvement number 2 about heavy flavors. In the AMPT model, the public AMPT model does not do a good job in heavy flavor production. And we have made recently several improvements about that. First is about the mini-jet cutoff. We know that we need the mini-jet cutoff because the jet production cross-section or the mini-jet cross-section will diverge if you do not impose a cutoff for massless partons. However, for heavy quark production, because of the heavy quark finite mass, the production cross-section is already finite. Therefore, you don't need a cutoff. And also in popular approaches like Funnel approach for heavy quark production, there's no cutoff for transverse momentum. Therefore, we have removed the P0 cutoff in hygiene, which is the initial condition for AMPT for heavy flavor productions. And also we realized that hygiene did not include the heavy flavor mini-jet or the heavy flavor production cross-section in the jet cross-section. That goes into the Glauber calculations. So, but we think it should be included. Therefore, we add the heavy flavor cross-section to the light flavor jet cross-section and obtain the total jet cross-section for the modified hygiene model. And after these modifications, we can calculate the CC bar cross-section for different collisions energies for PP collisions, and then compare to the world data. The data are the symbols, and the new improved AMPT model gives the black line. As we can see, the black line describes the data very well. This is the total cross-section for CC bar. The public AMPT, which before these improvements give the red line, which we can see severely underestimates the total yield. Therefore, and we can also realize that out of these different improvements, the removal of the mini-jet transverse momentum cut, P0, in the heavy flavor production is mostly responsible for the increase of the CC bar cross-section. And then recently in a study on small systems, PLED collisions, we have further improved the heavy flavor productions and hadronization in the AMPT model. So this is the structure of the string melting AMPT model, where we have the hygiene model, and then the energy, most of the energy in the overlap region is converted into quark and antiquark, which then enter the parton cascade. After they freeze out, we go through hadronization via quark coalescence, and then the hadrons go through hadron cascade and freeze out. In this work, we made the following improvements, as shown by the purple color. So first, we take the initial quark, heavy quark and heavy antiquark directly from the mini-jets, from the initial production to the parton cascade, without going through the string melting phase, because we think they they are perturbative and they should enter the parton cascade directly. And secondly, as will be shown later, we need the Cronin effect to describe the RPA of D mesons. So we added the Cronin effect to heavy quark in the initial stage. The Cronin effect just represents some transverse momentum broadening. And then for the hydronization part, we, in addition to the standard quark coalescence, we also added the independent fragmentation for heavy quarks and the anti-quarks. Then in this work, we studied the P-led collisions at LSC energies. And we found that the Cronin effect provides a possible solution to resolve the D0 RPA and V2 puzzle. So typically, up to now, there is a puzzle about the D meson D0 V2 at LSC P-led collisions. In that, the data for P-led RPA, the nuclear modification factor for D0, is pretty flat, as shown by the symbols, versus PT. However, the V2 of D mesons is significant. And normally, if we want to get a sizable V2, we need parton interactions for the heavy quark. For example, a heavy quark interaction with the light quarks at the magnitude of 1 millibarn or 1.5 millibarn in the parton cascade will give us a reasonable description of the D meson V2. However, if you have these interactions of the heavy quark, you will have the kind of jet quenching effect, which will suppress the charm PT spectrum at moderate to high PT, as we can see from here. So these two lines represent the effect of heavy quark interaction with the medium. So the RPA is going down with PT, which is not consistent with the data. And so that's typically the case. And vice versa, if you want to have almost a flat RPA, then you cannot afford to have a significant heavy quark interaction in the parton phase. And then as a result, your V2 of the heavy quark, heavy meson, D meson, will be small or near zero. And then you cannot describe the significant V2. So that's that has been the D meson puzzle. And we realized that if you put in strong enough Cronin effect, or this so-called KT broadening, then with the Cronin effect, these curves for the RPA will be enhanced to this kind of two curves, which is more or less consistent with RPA data. Because the Cronin effect is a momentum broadening in the initial stage, even after the heavy quark scattering in the parton phase, the broadening will enhance the RPA at a moderate to high PT, which will enable you to describe the RPA. And the Cronin effect, it turns out to have a small or little effect on the charm V2. Therefore, the RPA and V2 puzzle for D meson can be resolved if you put in a strong Cronin effect. So that's what we have done regarding the heavy flavors in the AMPT model. So let me proceed then to the third improvements, which is the local nuclear scale. So we have seen that if you look at the original AMPT long paper here, you can see that mostly it shows that the string melting AMPT model can describe the anisotropic flows and HBT well. However, it fails badly in describing the hadron spectrum, especially the PT spectrum. And in that paper, we already have shown a figure for the pion spectra in comparison with the finished data. The data are symbols, and the default AMPT model gives you the solid line, which describes well the PT spectrum. However, if you do the spring melting AMPT model, you get the other lines, which are too steep compared to the data. No matter what cross section you use for the spring melting model. So that has been a long problem for the spring melting AMPT model. Later, we realized the reason. It turns out to be related to the Lund parameters in the Lund symmetric string fragmentation function. This function has two key parameters, A and B. So here we write AL and BL to indicate it's a Lund parameter. The B parameter typical values are the following. So for in the AMPT early publication, the typical value we use is 0.5 in this unit. In PCA, 6 is about 0.6. In hygiene is about 0.9. So if you use these kind of values, you get this problem for the spring melting AMPT model. Then we realized in this study about 9 years ago that the string melting AMPT model could be tuned to describe the bulk data, not only d and dy, PT spectrum, also the anisotropic flows at low PT for central AA collisions if you are willing to use a very small value for B, as small as 0.15. You can see compared to the standard values is very low. And if you do that, then you can use the spring melting AMPT model to describe the data as shown here for RIC and LHC. If you think about it, it only makes sense because we know this relation from the original AMPT paper. The string tension, kappa, can be derived to be proportional to these Lund parameters. So basically, it's proportional to 1 over B. And a small b parameter indicates a higher string tension. So it's naturally to imagine a stronger color field being created in high energy AA collisions relative to PP collisions. And also, and then the stronger color field will indicate that the Lund B parameter should be small. So that has been, and in this paper, we just use a low value for AA collisions, much lower value than for PP collisions. And that has been the case up to this study, this recent study, when we introduced the local nuclear scale. So the problem is different values of the Lund B parameter are needed to describe PP and central AA collisions. And that is certainly unsatisfactory. And also, we have seen in the earlier improvement number 1 that the mini-jet cutoff parameter P0 needs to be different for central AA relative to the value in PP. And to take care of that, we have used A scaling as motivated by the CGC saturation model. So these two problems are similar, that these two parameters need to be different for PP and AA. And we roughly know why. We know the physical picture is related to the color field and its strength. It's also related to the CGC, which also relates to color field strength. Therefore, we propose a more general scale for these two parameters, because previously we have used different values for PP and central AA. Then you will ask, how about peripheral AA? How about smaller systems? Not a go-go, but oxygen, things like that. So to have a self-consistent picture, we introduce this scale called local nuclear scale, because we scale these two parameters according to local nuclear densities in the overlap region. And the densities are given by, there are two nuclei, right? And they overlap. So in the overlap region, in any space, you can evaluate the nuclear thickness functions Ta and Tb from the two nuclei. And then we introduce a scaling to decrease the Lund B parameter in AA collisions and increase the P0 parameter in AA collisions. Therefore, one is divided by the thickness function to some power, and one is multiplied by some other power. And this power, these two powers, describe how fast they scale with A, and also they depend on the collision energy root S. And they decrease or they change from the value in PP collisions. So the BLPP represents the Lund B parameter value for PP collisions. So we can first, we need to first fix these, the B value for PP collisions. So we can fit the charge hadron PT spectrum in PP collisions and determine the value for this B parameter value. And then we need to take care of the exponent functions, alpha S and beta S. And for that, we can use the high energy gold-to-gold and the lead-lead collisions at RIC and LHC. We can fit the mean PT of charged particles in these two colliding systems to fit alpha S and beta S at a few available energies, high energies. Then we can do an interpolation, and then we are done. So here is our description of the PP or PP bar charged hadron PT spectrum at a wide range of energies, and they are more or less reasonable with this constant B parameter for PP collisions. And then after we fix the local scaling, we can look at the Lund B parameter distribution in the overlap in the whole collision system, as well as the mini-jet cutoff parameters. So this is one event. At one central event, lead-lead collisions at 5 TeV. And this is the same event. So here we can see that for central collisions in the center, the B value is very low. And on the peripheral region is high. And it approaches the proton PP collision value as expected. And this is what we expect. And then you can also look at semi-central events and realize and see the similar behavior. And then for the mini-jet cutoff P0 parameter, we can see the opposite effect. In the center, the P0 value is very high. And if we think about the saturation scale, it's natural to expect that. And then in the outer region of the overlap region, then the P0 value is naturally much lower. So that's how we introduce the local nuclear scaling. Then we can look at the effect on the particle bulk properties like multiplicity and mean PT. So after the local nuclear scaling, the goal is we will be able to self-consistently describe any size dependence, including the collision system dependence and the centrality dependence for a given system. So for example, here is a plot of the charged particle DN data at mid pseudo-rigidity as a function of centrality for two systems, lead and gold. So using the nuclear scaling, we get the solid lines. And using the public AMPT model, we get the dashed lines. And they are more or less, the data are the symbols, and they are more or less both consistent with the data. However, the big improvements comes for the mean PT, centrality dependence. We know that for a long time, the mean PT of the public AMPT model is not correct. And you can see the data are the symbols again for the two systems, and the public AMPT model gives the dash lines. So this is the dash line to be compared to the solid symbols, and we can see it's totally off. Right? The data shows the mean PT goes down as you go to less central events, but the AMPT model shows basically a rising trend for LHC energies as well as RIC energies. With the local nuclear scaling, remember that the public AMPT model is using constant Lund B parameter because that was the case before. With the local nuclear scaling, the Lund B parameter automatically changes according to the overlap region and the nuclear thickness. Therefore, we get a totally different behavior. The Lund B parameter is no longer a constant. It's taking care of self-consistently, and as a result, we get the solid lines for LHC and for RIC, which is more or less consistent with the data, and much better than the public AMPT model. And then we can also look at the smaller systems, where the data have never been used in determining the local scaling parameters. So we can look at the xenon-xenon at LHC or copper-copper at 200 GeV, or P-lead collisions, even smaller systems, and look at similar quantities like charged particle multiplicity and mean PT versus centrality. And we can see that without any tuning, the AMPT model with local nuclear scaling is able to describe them consistently. So I think this work is pretty important because there are several key parameters for the AMPT model. There are basically four parameters: the Lund A model value, Lund B value, the mean jet cutoff P0, and the parton cross-section sigma. And they are all input values in the AMPT initialization file or input file. Now, with local nuclear scaling, these three are no longer free parameters. So they are determined by the scaling law. And so the only parameter basically left is the parton cross-section, which is reflection, which represents the QCD properties and the QGP properties, which determines, for example, the shear viscosity of the parton matter. So with this improvement, we can better focus on the study of QGP properties. Let me now go to the final improvement I'm going to show, which is the improvement of the parton transport. We know that in the string-matic AMPT model, the flow like V2, V3 at high energy most come from parton interactions, and which is described by the Boltzmann equations, such as here for two-body scatterings. However, we know that the cascade solution for the AMPT model, the ZPC parton cascade, or the similarly MPC parton cascade, they all have a problem in solving the Boltzmann equation, in that they are using geometric cross-sections. And as a result, they suffer from causality violation if the densities or the cross-sections are very large. And this can be represented by a so-called opacity parameter. Basically, it's a combination of the cross-section times the parton density. So if either or both are large, then the opacity is large. So naively, the cascade solution to solve the Boltzmann equation is only accurate in the dilute limit when this parameter chi is small. normally, naively, when it's smaller than 1, then the parton cascade will be correct. If it's much bigger than 1, it's expected to break down. And people have found that indeed it breaks down. And this chi parameter actually is defined to be the range of particle interaction, which is related to the cross-section divided by the mean free path of the parton. There's a way to cure the causality violation and recover the exact accurate solution of the Boltzmann equation. And this method is called the parton subdivision method, or sometimes called the test particles method. The method works because this Boltzmann equation is the right-hand side, the collision kernel is proportional to cross-section time 2 distribution functions. And if you do a transformation by multiplying the distribution function with a value, a larger than 1 value, and decrease the cross-section by the same value, if you do these 2 transformations together, then you can see that the Boltzmann equation remains invariant. Therefore, we're solving the same equation. However, if you look at the opacity parameter chi, it will be reduced by square root of this L factor. This L factor is called the subdivision factor. And so it means that we can do the transformation and reduce the opacity and and solve the same equation. Because the opacity is reduced, the causality violation is reduced. And eventually, with large enough L factor, we can remove the causality violation and get to the accurate result. So it's well known for a long time. However, there is a problem. It's well known that the subdivision method is very CPU consuming. It's very slow because you increase the parton number by a factor of L, and L is typically on the order of 100 or more. And then, binary collisions, you will have many more binary collisions. Therefore, the simulation is very slow. But more importantly, based on recent realization that small systems is important, and then event by event fluctuations and correlations are important. So more importantly, subdivision method changes artificially the parton number. It's basically splits one parton into many partons. Yes. Any questions?
Hello.
Hello.
好了。OK， 刚才好像有点问题，现在好了。OK。
You mean about my sound?
刚才没有声音，就是这页，这页。
Starting from which point? The beginning of this page or middle of this page?
Middle.
Oh, okay. Then I will talk about the subdivision method transformation again. How about that?
Okay, no problem.
Yeah. So okay, again, the way subdivision method will work is because the Boltzmann equation shown here is invariant if you do 2 transformations. First, you multiply the distribution function by a large factor L, and then you decrease the parton cross-section by the same factor. Because the Boltzmann equation is invariant, so we are solving the same equation and we should get the same solution. However, if you look at the opacity parameter chi, you will realize that the opacity parameter is suppressed or decreased by root of L. Therefore, the opacity is reduced. So if we use a large enough L, this subdivision factor, then we can reduce the opacity to a very small value where the cascade method works. And there we will get the same or the accurate solution of the Boltzmann equation. So that's how the parton subdivision will remove the causality violation and give accurate results. However, there are two problems. One, the subdivision method is very time consuming because we have many more partons per event. And then because we do binary collisions, at least, it's going to be very slow. And more importantly, recently we realized that, people in this field realize that event by event fluctuations and correlations are very important. And they are even more important for small systems. But parton subdivision changes these fluctuations and correlations because basically you artificially change a parton into many subpartons. And that is not good. So our goal is to improve the parton transport, in particular the ZPC parton cascade used by the AMPT model, not using subdivision, and see whether we can, how accurate the ZPC parton transport is, and if it's not accurate, how to improve it. So in the recent work with Xinli and Guoliang Ma and Yugang Ma, we have studied this for partons in the box. We have tested the ZPC, and we realized that parton cascade has certain freedoms when you do relativistic parton cascade, because you have freedom in choosing the two parton collision times and how to order the collisions. And basically, when you typically the parton collision is done in the two parton central mass frame. However, when you transform that collision time in the two parton central mass frame to the parton gas rest frame, you will have two different collision times for the two partons due to the Lorentz transformation. That's called the collision time 1 and collision time 2. And therefore, if you want to do the collision in the rest frame of the gas, you have to choose what time do I use. For example, you could use the average time, you could use the minimum time, maximum time, or anywhere in between. And the standard ZPC uses the minimum, the average time. So that can be called the T-average scheme. And we found, if you put gluons in the box and make it dense so that the opacity is 2, we start the parton gas in the off-equilibrium momentum distribution represented by the dot dash line. And then you let it scatter and evolve, and it should go to the Boltzmann thermal distribution, which is this solid line. However, we realized that the standard ZPC gave us the red line, which is off. You see there's the same number of partons, but the momentum distribution is off. So the default ZPC or the T-average frame scheme cannot maintain the thermal equilibrium at high opacities. And then we tested around with different choices of these times, and we found that this a new scheme that uses the minimum time, the earlier time, for the collision and the ordering, gives reproduce well the thermal distribution. So if we choose this minimum time, then we will get a black line, which basically reproduces the thermal distribution. So this is a much better choice. We also look at the viscosity of this method, this new collision scheme, which gives us the black line results for the H/S for the parton for the gluon gas for different opacities, from small opacity to large opacities. And then we can compare with the for isotropic scatterings, we have the Navier-Stokes excitation. There's a formula which is almost exactly correct. for isotropic scatterings. And we can compare with this orange line, and they are pretty close. So we can say the new scheme reproduces the opacity or the shear viscosity H as well as H over S well, up to very high opacities like 40. There's a super high densities or cross sections. But if we look at the default ZPC, we get the red line, which will, at low opacities, as you expected, is still correct. But when you go to high opacities, it starts to go off. So default ZPC also fails in describing the shear viscosity. And in this work, we also look at the time evolution of the gluon gas, how the variance of the pitch spectrum, or basically the width of the pitch spectrum, changes with time. And we see that if we do parton subdivision, we get the green line here, which is supposed to be the correct solution. And if we do the newer scheme, we get the solid line, which is very close to the subdivision results, much better than the default ZPC. Therefore, we have found a new collision scheme that is much better than the default ZPC scheme. Then more recently, with a student at ECU, Todd Mendenhall, we have done a new check and improvement of the ZPC parton cascade, because recently people have found the exact solution of the relativistic Boltzmann equation. There are certain limitations, so it's only solved for massless homogeneous gas and the two-body isotropic scatterings. But we can do that with ZPC, and then the good thing is this is an analytical exact solution for off equilibrium evolution toward equilibrium at any time. So we can test the ZPC against the full time evolution in the momentum spectra and try to improve the ZPC accordingly. And for that less expanding space-time, the solution is given by the following. So you see, it depends on the 3 momentum P. It depends on time tau, which is proportional to the real time t, etc. And if we plot the momentum spectra versus the momentum is scaled by the temperature, then we see the following. So we have divided the momentum at a finite time tau over the equilibrium momentum spectrum. The equilibrium spectrum is just the standard Boltzmann thermal distribution. So we can see that ZPC gives you the symbols, and the theory gives you the solid line. Of course, we start our initial condition at time 0. According to the exact solution, we are exactly agreeing with the theory. That's no surprise. However, when we evolve to finite time at a tau value of 2 or 4 or 6, we can see that the exact solution are again the solid lines, and ZPC give you the symbols, which more or less well describes the time evolution over the whole momentum spectrum. At much later time, tau of 60, the system will reach equilibrium, the thermal equilibrium. So the theory curve is basically flat at 1 because it's divided by the thermal distribution. And the ZPC result is, again, the symbols, which you can see has a certain deviation. However, the deviation is not big. It's a few percent level, all the way to large momentum. So this is using the previous new scheme, the T minimum scheme. So we can see that GPC with T minimum scheme performs quite well against the exact solution. Then we can we also use the more general scheme. We can make a more general collision scheme by choosing an intermediate collision time, where the T mean scheme just corresponds to this parameter R being 0, and the bad scheme, the default GPC scheme, corresponds to R value of half. And then we can optimize the R value to minimize the deviation. And due to time, I will be quick. So basically, we see that if you do this general scheme, we can further reduce the spectrum error. This basically one means exactly agreeing with the analytical solution, and the new scheme gives us the solid lines for different opacities. And our general scheme gives us the dotted lines or dashed lines, which are much closer to 1 than even the previous new scheme. Therefore, we can improve the GPC transfer more by making these more general schemes. So I think I will skip basically this slide just by saying that currently the causality violation in AMPT is small because the cross-section is small. However, if we want to describe finite temperature QCD, kinetic theory, we need to change the cross-section according to the screening mass, because the screening mass is temperature dependent. Then the cross-section can be larger near the phase transition, near the hadronization, where we have to worry about causality violation. However, these new schemes will suppress, as we can see, the new schemes are very good in suppressing the causality violation, therefore giving us accurate results even when we are at high opacities. I have shown 4 improvements, and I have skipped other recent improvements, which I list here. For example, fix of the electric charge conservation that's done together with Guo Liang a few years ago, and other work, which I have to skip. Let me get to my summary. Basically, AMPT model provides a kinetic theory description of heavy ion collisions, and is well suited for non-equilibrium studies. And we have made recent improvements to make the AMPT model more versatile and accurate. And that lays a foundation to further develop AMPT or the GPC parton cascade into a dynamic model of finite temperature QCD kinetic theory. So that's all. Thank you very much. And I will finally show a few pictures of the students at ECU and also visiting scholars who have been to ECU. Thank you very much.
Thank you, Professor Lin, for his wonderful talk. And many people, including myself, are using Professor Lin's AMPT program. So many thanks to Professor Lin for his contribution to our field. So it's great to see the continuous development and improvement of the AMPT model. And thanks to the efforts of Professor Lin and his collaborators. Next, please raise your hand or just open the microphone for questions. So you can ask a question in English, either in English or in Chinese.
Hi, Zui. Can you hear me? Yeah. May I? First, thank you very much for the nice talk on the improvement of AMPT model. Maybe I ask the first question is how, when you're discussing a different T scheme in the parton cascade, how would that we see it has a very dramatic effect on the PT spectrum in the long expanding case. How would the different T schemes affect the physical observables in the relativistic heavy-ion collisions? Do you have some results or information?
Yeah. We have shown basically in the parton cascade only studies that some observables are severely affected if you are at very high densities, right, or opacities.
Mm-hmm. Yeah.
But those densities are very high, like 700 MeV temperature and 3 millibar cross section.
Mm-hmm.
For the standard AMPT model simulations, the causality violation is small. This has been shown by Danish Mona in this publication or in this paper. Because the temperature is much lower, let's say maybe 500 MeV at most, and cross-section is small. So we are using no more than 3 millibar cross-section. And he has not done different schemes, but he is using the default scheme, which we have shown to be bad for high densities. But he has used the default scheme and compared to subdivision results, which are supposed to be correct. And he found that for V2, the effect is small. So that suggests the effect is currently small for normal AMPT simulations.
Is that related to the fact that when the fiber, because the fiber expands very fast, so the density also it decreases very fast as a result?
Yeah, this opacity parameter chi is a product of the density and cross section. So for standard 3D AMPT simulations, cross section is fixed. Let's say 3 or 1 millibar for parton cross scatterings, but n, right? The density is the maximum at time 0, and then it goes down quickly. So the effect is, like I said, is a convolution of the time history. So at the beginning, chi, this opacity may be 1 or 2 at most, but then it decreases fast. So the overall, that's partly the reason that the overall effect is small currently. However, what I want to say is, if we go beyond this, right? If we take a finite temperature QCD field theory, then cross section should no longer be constant. Even if we want to have a constant 8/s for the parton matter, it will mean that our cross section should be temperature dependent, and it will basically rise strongly with temperature as you go toward the phase transition, and then the opacity will not drop, may not drop at all with time in the expansion, and then the causality violation may be worse.
Yes, indeed.
Yeah. Fortunately, this improved collision scheme can still be better to suppress it.
Yes, I agree. Yeah. Okay, thank you very much for your nice explanation. Thank you.
Yes, can you hear me?
Yes.
Okay. Thank you very much, Professor Lin. Very nice talk. So I see we already had a lot of nice developments in solving the RPA and the V2 puzzle for D0. So it works very well. But on the other hand, we know that we also observe the high PT and jet particle V2 in PLED, but with unit RPLED. So it's also a puzzle. So I'm wondering that if this development also work for high PT particle or jet in small system. For example, like late jet parton shower happens in CVC instead of before in stream melting or introducing the fragmentation and so on. Like what you did in the D0 issues. So do you have any comments about it? Thank you.
Yeah, we have not done light flavors or jets in RPA. So we cannot address that quantitatively. But for heavy flavors, maybe it's a little bit easier to do that because we know heavy flavors are produced by PQCD, so we know the production pretty well. But for light flavors, maybe it's more complicated. Light flavors, first you have you have soft process which can extend to certain PT, certain moderate to higher PT. And also another problem is we don't have inelastic energy loss in AMPT whatsoever. Here we only have elastic energy loss in ZPC, and for heavy flavors, there are studies that show that the radiative energy loss will take over at quite high PT. So below that PT, when we only have elastic energy loss, our results are still more or less reliable. But for light flavors, that PT scale goes down a lot. So it means that we cannot address, we can only address to a lower PT if we do light flavors with this similar approach.
Okay, thank you. But anyway, I think this is a very good direction that we can do something further development for light flavors in the future. Okay.
Yeah.
So any other question? Li Fei?
Hey, thank you, Professor Lin. I have a question about the initial state in AMPT. I mean, are the initial protons and neutrons the same? If we set two kind of nuclei with same mass but different charges, like isobar collisions, would there be isospin difference?
Yes, certainly. I did not mention the recent work, for example, here done by Hao Jiexu and Fuqian Wang and others, where we have used the DFT densities in AMPT simulations, where the proton and neutron density profiles versus radius are different, for example. And so, but so you can take an arbitrary profile, whichever nucleon density profile, which can be different for neutrons or protons, and put into the simulation. One can also use deformed nuclei with nice spherical shapes. So and they all will lead to certain differences of isospin or charge, proton neutron ratio of the incoming nuclei. So for the isobar, I have done a lot of studies, including work from Jiang Yongjia and who have seen this kind of effects.
Okay, thank you.
Bai Xiaozhi老师.
Thank you very much for the very nice presentation, Ziwei. Yeah, so I have a question. So because AMPT already can describe open heavy flavor, so my question is, do you have any plan to make some further development to net AMPT to describe the quarkonium production? Yeah, thank you. This is my question.
Yeah, currently there is no such a plan. Of course, if a collaborator or former visiting scholar have interests, we could discuss it. So currently we are confined to open heavy hadrons, like including both mesons and baryons. One could extend it to heavy quarkonium, but I guess maybe more work will need to be done. For example, survival of the primordial quarkonium in the QGP phase, depending on the binding energy, etc. Right? Those are new effects not present for open flavors. So yeah, it could be tried.
Yeah, okay, thank you very much.
So I have a question. How to understand the choice of the new scheme, different scheme, the collision time, can affect the thermalization on a physical picture?
Yeah, the collision time, for example, yeah, the collision time, and not only the collision time, but also the collision ordinary time. But anyway, collision time specifies how GPC performs each collision. And if you use naively, if you use the default scheme where you use the minimum, the average time, you get one result. But if we use the new scheme, which uses the minimum time, we will get another result. Now, when we use the minimum time, of course, the minimum time is earlier than the average time. So the collision will be somewhat earlier for each collision, and the collision rates will increase a little bit. And people have found that the default scheme, due to causality violation, under predicts the collision rates. Therefore, when we use the minimum scheme, T minimum scheme, it increases the collision rates, and we check the collision rates, and the new collision rates agrees better with the exact expected collision rates. And that's part of the reason why it gives a better results, I think.
So does the collision take time, or the collision happen earlier? So for the each next collision, GPC proceeds from one collision to the next according to a collision ordering, order the list of the collisions. So so after it's done one collision, for the next collision, the new scheme will do the collision earlier than the default scheme, right? Because for the next collision, both CT1 and CT2 are fixed, and then if we choose the minimum, it will happen earlier. Okay. So
and this goes for all the
collision take time. So
the collision itself,
yes,
the collision is not considered to take time.
Okay.
Is considered to happen in the same time in the global frame of the gas, and without taking any time duration. Of course, it doesn't mean that the partons, actually the produced partons also are not given any formation time. They can collide immediately after.
Okay.
But you need that, otherwise your collision rates will be wrong.
I see. So any other question? So I can't see any new questions. So if there's no new questions, let's thank Professor Lin for his great presentation again. We look forward to meeting Professor Lin soon.
Yeah, hopefully soon at some conferences. Thank you very much.
Thank you.
Okay. Bye now.
Recording
好的
stopped.
Okay, I can stop the sharing.
好的。好，那紫薇，是你那边比较晚了，你早点休息好了。
OK， 好。
Yeah.
OK， 好，谢谢国亮主持。
也谢谢你啊，谢谢给我们两次这个lecture， 非常感谢。
没问题。Yeah。
期待不久相见了。好。
Yeah, then maybe see you in sometime in summer.
Yes.
Yeah. Okay. Yeah.
Hau,
Here. Bye.